Welcome back to Star Studies, everyone. In the last episode, you'll recall that we went over how we can study stars in space by using their spectrum of light. And you'll also recall that from a very visual standpoint, a star's spectrum would look something like the spectrum shown at the top here. And it's pretty much what we often call a rainbow. Except that in astronomy, a spectrum can include much more than just light that we see with our own eyes. In my research, for example, we used infrared light. And a star spectrum also includes the dark narrow lines that you see here as well. And from a scientific research standpoint, we actually need to quantify the brightness of these dark lines in order to fully understand the star. And the way we do this is by using a graph of the spectrum where we graph the brightness of the light as a function of the light's wavelength. And that basically looks like what's on the bottom here. And this spectrum might look quite messy at first to you, but once you zoom in, you can tell that there's actually a lot of structure here, where there are very noticeable dips in the brightness of the light at very precise values of the light's wavelength. And in this episode, I'm basically going to explain how a star produces the light that we use to get its spectrum, and what causes these dips. So, let's start off by asking a question that you've probably asked yourself before. How does the sun shine? And that's actually a question that people have asked for a very long time, and it's only within the last 100 years that we really figured it out. And the answer is pretty simple. In general, stars shine because at their core, a process called fusion takes place. Now, for stars like our Sun, fusion is basically where we have 4 hydrogen atoms that collide to form a helium atom. Now, the actual process is actually a little more complicated than this, involving neutrinos and a couple other things, but overall, this is what happens in the core of stars. And if you look at the mass of a hydrogen atom and multiply it by 4, we get the total mass before the reaction, since we started out with 4 hydrogen atoms. Now if we subtract the total mass that we have after the reaction, which is just the mass of the helium atom, we notice that there is actually a very small amount of mass left. And that mass is the mass that goes into the famous equation E equals mc squared. And that energy that's left over is what goes into producing light as another output of fusion. Now this is a picture of the sun and the different layers that it has. I got this off of Wikipedia because it is a pretty good visualization of the sun's structure. Regions 1 and 2 are basically where that fusion reaction that I just described takes place. And the pieces of light that are produced in fusion, which is what we usually call photons, I've drawn there to be 3 of them produced here, then travel outward through region 3 and through the star's outer atmosphere, represented by regions 4 and 5 here. At this point, most of the light actually continues and is completely emitted as light that makes it to us. But some of the light is actually absorbed by the atoms in the star's atmosphere. And here I've drawn it so that only 2 of the 3 are able to make it through. And how likely a photon is to be absorbed when passing through regions 4 and 5 depends on the photon's wavelength, as well as the chemical composition of the star's atmosphere. And to understand this, we actually need to review over the basic structure of an atom. And if you're curious, regions 6 and 7 just represent the chromosphere and the solar flares of stars. So, the basic structure of atoms. You've probably been taught about this model of the atom, where there is a central nucleus with protons and neutrons, and that there are electrons orbiting that nucleus. and that these orbits are each at a fixed radius from the nucleus. You probably also remember that each orbit has a particular energy level associated with it, and can have up to a certain number of electrons in that orbit. This overall is what's called the Bohr model of the atom. Now, with our understanding of quantum mechanics these days, we actually know that this model of the atom is wrong. But we still use it, and it's still taught in schools, because some of the basic ideas are correct. And if nothing else, it's at least much simpler to understand than the quantum mechanics model of the atom. And by the way, quantum mechanics, in case you're wondering, is basically the laws of physics that describe the universe on a microscopic level. The main thing that is correct about the Bohr model is that the electrons have discrete energy levels. And these energy levels are actually different for every element in the periodic table. So here is what represents the hydrogen atom. And for the hydrogen atom, these energy levels are 13.6 electron volts, 3.4 electron volts, 1.5, 0.85, and so on. And this electron is actually illustrated to be in the lowest energy state here, or we often call that the ground state. And when we have a photon come in, that electron can absorb that photon. But in order to do that, the photon must have precisely the right amount of energy to make the electron jump to another discrete energy level. So, to illustrate this, let's say we had an incoming photon that had an energy of 10.2 electron volts. And 10.2 is actually the difference between the ground state energy and the first excited state energy, 13.6 minus 3.4. In that case, the electron that's in the lowest energy state can absorb that photon and jump to the first excited energy state. And if after that we have another photon come in with an energy of 1.9 electron volts, the difference between the first excited state energy and the second excited state energy, then again, the electron can absorb it and jump from the first to the second excited state. And if the original photon, let's say it had an energy of 12.1 electron volts, that's the difference between the ground state energy and the second excited state energy. Then the electron would be able to absorb that photon and jump from the lowest energy state to the second excited state, and so on. But if instead we have a photon with an energy of something like 5 electron volts, the electron would not be able to absorb that photon, because there are no two energy levels for the hydrogen atom that have 5 electron volts as the difference between the two energy levels. And in that case, the electron would not absorb the photon, and the light would just pass right through the atom. So overall, what I'm getting to is the fact that when a photon is produced at the core of the star and travels outward through the atmosphere of the star, in order to be absorbed, that photon can only have precise amounts of energy. Not just any photon with any amount of energy can be absorbed. And since the energy of a photon is determined by its wavelength through this equation right here, where h and c are just physical constants, if an absorbed photon can only have precise values of energy, then that means through this equation that it can also only have precise values of its wavelength as well. And these precise wavelengths are actually different for each element in the periodic table, but fortunately, we understand quantum mechanics so well these days that we know which wavelengths correspond to which elements. So, This all explains exactly why, when we look at the spectrum of a star, this one that I'm showing you right now being part of the infrared spectrum of the sun, that we see these dips right here. Very precise values of the light's wavelength, which is shown on the horizontal x-axis here of this plot, where the light coming from a star isn't as bright. Each dip that you see here represents one of those precise wavelength values that matches with the difference between energy levels of some element in the periodic table, just like we talked about. And the light is not as bright at those wavelengths because some of the photons that were produced with that wavelength at the core of the star were absorbed by the star's atmosphere and didn't make it to our telescopes. Now, the scientific way that we often refer to these precise values of the wavelength is absorption lines. And here there are about 5 absorption lines for iron, a couple in the middle for silicon, and a few more for sulfur as well. So, by now I'm hoping that you understand what a star's spectrum is, and particularly what these dark lines, or absorption features, in a spectrum represent. And you might be wondering, what in the world does this all have to do with astronomy? But just wait until the next couple episodes, and I'll explain how we can use what we've gone over so far to learn so many different things about stars. So, as you take in all of this science, may the force be with you, and I will see you next time on Star Studies.